My name is Phuc Nguyen. Good morning, everybody. First, some words about our background and current status of benefits and scope of selective breeding in aquaculture. I have been involved in aquaculture research since 1971. Our program was started by Professor Harald Skjervold at Agriculture University of Norway, now University of Life Science. In 1984, Institute of Aquaculture Research, or Aquaforsk, was established. As our work with selective breeding became known, we got involved in a number of breeding projects internationally. Together with Aquaforsk Genetics Center, these programs has been further developed and improved. In 2008, Aquaforsk became a part of Nofima. My topic now is selective breeding so far, possibilities, achievements, and in major industries. The first question I will raise is, why should we change a population? There are several reasons. Wild fish has low survival in captivity. They are stressed, some are cannibals, and so on. Further, to increase productivity, of course, the most important reason, and to help improve the welfare of farm fish. Doyle 1983 state, selection for major traits will facilitate domestication and improve the welfare of farmed fish. As far as I know, as far as I see it, production based on wild animals are not sustainable in the long run. So the question is how to improve a population. We need some backgrounds before starting a breeding program. We need knowledge about reproduction of the species in question, how to produce broodstock, spawning, fertilization of eggs, hatching, and start feeding. We also need to have methods to record economic with high repeatability. These traits should be based on the breeding, should be in the breeding rule. We need to tagging and identification of animals and information about genetic and phenotypic variants of populations. Further, we must define the breeding goal for a population. Our traits of economic importance should be included in the breeding goal. Some examples are body weight at harvest, major diseases, survival, meat quality traits. It is important that increasing the number of traits in the breeding goal will lead to a reduction in genetic gain per trait. We need a lot of information about the traits in the breeding goal. I will mention some of them. For each economic trait included, we must know the phenotypic and genetic parameters like average, mean, standard deviation, variance, heritability, genetic variance, phenotypic variance, correlations between traits, phenotypically and genetic, and economic value of the trait. What is the status of breeding program in aquaculture? It is estimated that it was estimated that about 8.2% of aquaculture production was based on selected bred animals. Naira and Raya 2010, and myself et al. 2011. Only 8.2% had family-based breeding programs. The only species that used 100% selected bred animals was Atlantic salmon. Today, this figure is hopefully higher, but how high is not known. In addition to family-based breeding programs, there are some breeding programs applying just individual or phenotypic selection and crossbreeding, but the number is not known. From a breeding point of view, in aquaculture, it is a problem that with the very large number of farmed species, according to FAO statistics, there are around 40 species farmed. So let us take some examples of genetic improvement programs. And we will have a look at Atlantic salmon and Nile tilapia. The breeding program of Atlantic salmon was started by Phuc in September 75 for Atlantic salmon in Norway. The wild broodstock were sampled from 41 rivers, strains. Mating the first generation was within strains. Later, highest yielding strains were selected and crossed. The first 2 generations of selection was for growth rate only. We wanted to demonstrate the effect of selective breeding for growth rate. Later, age of sexual maturation, diseases, and carcass quality was included in the breeding goal. What has been accomplished for Atlantic salmon? What genetic gain have been obtained? And I tell you, the first generation of selection, the genetic gain was 15%. And this was much higher than we really dreamed of. And really, it was very high, this 15%. After 5 generations of selection, feed consumption was also recorded. Thoresen et al. 99. And the following differences between wild and selected fish was as follows. The growth rate was increased with 113%. Increased utilization of protein, 9%. Increased utilization of energy, 14%. And reduced feed per kilo growth was minus 23%. After 11 generations of selection, my estimate is that reduced feed per kilo growth is at least 30%. If that's true, it means that 0.7 to 0.8 billion US dollars is saved in feed cost each year in Norwegian salmon production. That's quite good. So what has been accomplished for Nile tilapia? In 1988, ICLARM, now World Fish Center, and Phuc started a selection program for Nile tilapia at the research station at Muñoz, Philippines. A base population of 4 African strains and 4 strains farmed in Philippines was established. This was the base population for us. Selection was for growth rate only. I wanted to demonstrate that it is possible to get genetic gain for a tropical fish. And genetic gain after 5 generations of selection, with a generation interval 1 year, was 85%, or 17% per generation. Impressive. So what has been accomplished for Nile tilapia? This genetically improved fish was named gift tilapia, genetic improved farmed tilapia. The gift fish is now found in several countries: China, Southeast Asian countries, and America. The breeding program has been continued. With the present increase of production, 13.3% per year, Nile tilapia is likely to be the species with highest production in 2020. Informant states that the majority of the present Nile tilapia production has gift genes. So I will show you results from a review of genetic gain. Here, different traits, genetic gain percent, number of estimates, and generation selected. And on the top here, 67 estimates of body weight, increase in body weight, 12.7%. I was most impressed of that high figure. But look at further down for different disease traits like IPN resistance, Vibrio salmonidicida, and Taura syndrome. Very high response to genetic gain. We'll come back to that. And there I thought it would be nice to compare something with these fantastic genetic gains obtained with what is obtained in farm animals. And looking at Norwegian sheep and pigs show the following estimate. Norwegian Northwind pigs had a genetic gain in growth rate of 4.5% per generation. Andersen and Ramberg, 2013. Norwegian white sheep lamb had a genetic gain in carcass weight of 2.5% per generation. H. et al., 2009. So for what we have obtained for genetic gain in aquatic species is far above what is obtained for farm animals. I want to stress the production of aquatic plants. Although we have focused on fish and shellfish, attention should also be paid on aquatic algae and plants. It is estimated that the amount of microalgae and sea plants produced in the ocean is about 200 billion tons per year. Unbelievable. Currently, only 0.3 parts per million is harvested by fisheries and sea plants. In New Zealand, a breeding program for green shell have as high genetic gain as for Atlantic salmon for growth rate. An important task for future research will be to harvest the enormous primary production in ocean by producing genetically improved shellfish and sea plants. Some concluding remarks. our goals should be that all aquaculture production should be based on genetically improved stocks. It has been shown that it is possible to double growth rate in 6 to 7 generations of selection. It's also possible to develop strains resistant for major diseases by selective breeding. In the future, we need to focus on farming genetically improved aquatic plants and algae. I thank you for listening. Good luck to you for working in aquaculture farming, for increasing production of food and, I stress, healthy food for the human population. Good luck to you, everybody. Thank you.